Hi, everyone. So today we are going to go over um, quadric surfaces, which is part of our Calculus 3 curriculum, also known as multivariable calculus A, um, Math 213 at the CCNY level. All right. We have 6 objectives during this lesson. The first one being able to work with traces. The second being able to identify quadric surfaces based on an ellipse, and then based on a hyperbola. Then we'll be able to identify cylinders, identifying graph quadric surfaces, and then last but not least, we'll be able to find the curve of intersection of two surfaces. So throughout this lesson, I might pause the video and then share my laptop screen of visualizations of the concrete examples that we go through so that you can really see these 3D images from all different types of angles. Right. Our motivation for this lesson, we have the following. In the section on 3-space, we saw that the graph of a linear equation in 3 variables is a plane in space. In general, the graph of an equation in 3 variables, and this is our notation, f of x, y, z is equal to 0, is a surface in 3-space. And so in this section, we're going to be studying surfaces called cylinders and quadric surfaces. And we'll be doing loads of concrete examples. I think there's 8 in this section. And I have it all in order to just save time. I pretty much have the notes all written out, but they're hidden. So as we go through each step, I'll make them visible for you guys to see. Okay, so our first objective, we're going to work with traces, which if you guys have taken linear algebra before, which I believe you guys have up until this point, we've dealt with traces in that course too. So we have, just as we can use the x and y intercepts of a plane curve to help us sketch the graph of a plane curve, we can also use the traces of a surface in the coordinate planes to help us sketch the surface itself. And so now we have our definition. The trace of a surface S in a plane is the intersection of the surface and the plane. So why don't we go ahead and maybe highlight this? And so in particular, the traces of a surface S in the XY plane, the YZ plane, and the XZ plane are called the XY, YZ, and XZ trace. And so how do we find trace? To find a trace of a surface, what we're doing is we're fixing one of the variables to a constant value, and then we're sketching the resulting curve in the plane formed by the other 2 variables that are left over. So if we wanted to find, for example, our XY trace, that missing variable z, we set z equal to constant value. 0 is a relatively simple one to deal with. And then we sketch the graph of the resulting equation in that XY plane. So we'll be practicing that a lot in our first example, which is on our next slide. And then there's one last sort of comment I want to make. If the surface does not intersect the plane, then we have no trace. There's no trace in that plane. Okay, so again, trace representing intersection of the surface and the plane. So our example 1, we are given the plane 4x plus, oops, sorry about that, 4x plus 2y plus 3z is equal to 12. And we want to find the traces of the plane in the coordinate planes, and then we want to sketch the plane. So how do we find the traces of the plane in the coordinate planes? Well, we're dealing with 3 different intersections. Our YZ plane, our XZ plane, and our XY plane, aka our YZ trace, our XZ trace, and our XY trace. And so in this first column, we want to set our, what's our missing variable here, x. We set that equal to 0, and then we want to find the trace for YZ from there. So we look at our plane equation. 4x plus 2y plus 3z is equal to 12. We have that written out right below. Let me reveal it for you. I think I already canceled out the 0. So what do? We set x equal to 0. And when x is equal to 0, then that whole first term 4x cancels out. And what are we left with? 2y plus 3z is equal to 12. Okay, now what do? We want to isolate one of the variables so we can sketch this out and see what it looks like. So why don't we isolate our y? We'll subtract 3z from both sides and then divide everything by 2. And then we'll end up with our second column, or second sort of revealing. And we get y is equal to negative 3z plus 12 over 2. And we can also write this as just negative 3/2 z plus 12 divided by 2 is just 6. And there we have it. This is our trace in our YZ plane. So from here, what we can do is we can identify some intercepts. And so what does that mean? Well, we know that x is equal to 0 every single time. But what if we set z also equal to 0? What would we end up getting our y value to be? Well, if z is 0, this all shoots to 0, and then we get our y is just equal to 6, which is what we have down here. 0, 6, 0 is one of our intercepts. And then what's another intercept? Why don't we now set y equal to 0 and then solve for z? So subtract 6 from both sides. Then we're going to multiply both sides by 2. So now we're looking at negative 12 is equal to negative 3z, and then divide both sides by negative 3, and then z is equal to 4. So x is 0, y is 0, and now z is 4, which is what we have down here. And so these are our intercepts for our YZ plane. Now, why don't we jump into the second column? Procedure is going to be exactly the same. So we're going to go a little bit faster with this. And what are we going to start off with? Since our y is 0, now 2y cancels out, and we have 4x plus 3z is equal to 12. And then from here, let's isolate one of the variables. Why don't we set this all equal to z? Z is equal to what? So subtract 4x from both sides, divide both sides by 3, and what do we end up with? Z is equal to negative 4x plus 12 over 3. And then we can also just rewrite this as z is equal to negative 4/3 x plus 12 divided by 3 is just 4. And so this is our trace in our xz plane. Again, now let's find some intercepts so that we can really get a visual of how we can sketch this out. And so why don't we first let x be equal to 0? Y is always going to be equal to 0 in this second column when we're dealing with our xz plane. So plug in x for 0 and we get z as 4. So we once again get 0, 0, 4. And then the last one, let's now have z equal to 0, and why don't we solve for x? So when z is 0, subtract 4 from both sides, get negative 4 equal to negative 4/3 x, multiply both sides by 3, negative 12 equals negative 4x, divide both sides by negative 4, and we get x is equal to positive 3. So how do we write this? 3, 0, 0, and we'll just reveal it. Perfect. Last but not least, let's look at our trace in our xy plane. So now we're going to cancel out this 3z up here. Oops. So we're looking at 4x plus 2y is equal to 12. And then let's once again isolate our y, subtract 4x from both sides, divide both sides by 2, and we have y is equal to negative 4x plus 12 over 2. This can be rewritten as negative 4 divided by 2 is just negative 2. So y is equal to negative 2x plus, and then 12 divided by 2 is just 6. So negative 2x plus 6. And that's our trace in our xy plane. Last but not least, let's find our intercepts here. So z is always going to be equal to 0. Why don't we set x equal to 0 here? That way we easily can find that y is just 6. So we have 0, 6, 0 for our first intercept. Feel that? And then finally, for our last intercept, why don't we set y equal to 0 and then solve for our x value. So when y is 0, we're looking at negative 6 equals negative 2x, divide both sides by negative 2, and we get x equals 3. So our revealing is 3, 0, 0. And that's it. So what does this tell us? You can notice that there are some intercepts that have been repeated. So we have a 0, 0, 4, we have our 3, 0, 0, and then we have our 0, 6, 0. So we really have 3 intercepts. And so what's happening here, we have 3 intercepts. So we have like a triangular region that creates a plane, and that represents that sort of intersection area. And so how do we sketch this out? We just have to plot 0, 6, 0, 0, 0, 4, and 3, 0, 0 on our X, Y, Z graph. And so when we do that, and again, I sort of just stated this, these are the plane passes through these intercepts. And so when we sketch out this triangular region, joining these 3 points, we end up getting the following. This orange triangle, which when we extend the entire plane, it just shoots out into infinity in each of the directions. Don't judge my graphing. I am not very good with sketching this out. So what I actually did was I also inputted it into a CAS program, also known as a computer algebra system. So GeoGebra, I don't know if any of you guys know that system. It's great. It's free. You can do it online. And when I plugged that in, this is what we get. And so this is a much better representation, really seeing how that plane, this triangular region, really extends in all directions. And that's it. So that completes our example 1. And now, or I'm going to pause the video so that I can show you the sort of all angles of this intersection. So give me a second. All right, so here we have our plane, and then if you notice, I can like really move it around. And so you can see all different angles. That our plane passes through these intercepts over here. And the intercepts form that triangular region. It might be a little difficult to see the triangular region, but you could see some of the intercepts, right? Our 060 is right here. And then our 004, and then our 300. So our 004 is right down here. Our 060 is over here. And then our 300 is over here. So these are all the intercepts that form a triangular region, but you really can't see that triangular region formed that well here. But yeah, all right. Okay. So let's move on to our second example. And so there are 3 parts in this example. We have let S be the surface defined by Z is equal to X squared plus Y squared. And we find that this surface is the standard circular paraboloid. Again, you'll be able to see some visuals real soon. But what are we asking to find? We want to find the traces of S in the coordinate planes. We want to find the traces of S in the plane Z is equal to K, where K is a constant. And then last but not least, we want to sketch this surface S, this paraboloid. Right, how do we find trace? Again, look at the 3 planes, X, Y, Y, Z, and X, Z, and then set that third variable equal to 0 to find your equations. So in the first case, we set 0 equal to Z, and so we're looking at our X squared plus Y squared equals 0. And then from here, we get that we really have only just 1 point, 1 intercept, because if we set y equal to 0, then we get x squared equals 0, and the square root of x squared is x, and the square root of 0 is just 0, and then vice versa. We set x equal to 0, then we have y squared equals 0, and then our only solution here is once again 0. So we're looking at only 1 point, reveal this, which is 0, 0, 0. And this happens to be our vertex point. Okay, now let's look at our YZ plane. We're setting x equal to 0 now. And so we have z is equal to y squared. And then from here, if we set our z equal to 0, then we get y squared is equal to 0. Once again, have square root of 0, which is 0. But then if we set y equal to 0, we get z is equal to 0 squared, which means we should keep this variable oriented. And so what we're going to do is if our z is equal to 0 squared and our y squared is equal to 0, then what is our coordinate point? If we have y is our y coordinate point, then our z is just y squared and our x is just 0. So the point we're looking at is 0, comma, y squared. Okay. And we're going to do a very similar manner for our xz plane. And so we have when y is equal to 0, we have z is equal to x squared. Again, let's keep it variable oriented here. We have our y is 0, z is x squared, so let's just let x be x. So x comma 0 comma x squared. Okay. And part B now is saying find the traces of s in the plane z is equal to k, where k is a constant. And so I'm going to use a subscript K1 when we're dealing with z is equal to k. So why don't I maybe write that in over here? Just because then I'm also going to show K2 and K3 when we're dealing with x and y. Okay, so x squared plus y squared is equal to z. We're going to let z be our k1 here. So x squared plus y squared is equal to k1. And then what do we have? Well, x squared plus y squared is just a circle if it's equal to a constant, and that constant, that square root of the constant, is just the radii of the circle. Obviously, we are dealing with positive values because radii can't be negative. So we want our ki to be greater than 0. And then we have a circle with a radius of the square root of k1 in our plane. Z is equal to k1. Okay. And this is our only horizontal trace that we are going to be looking at. Okay. So think of a circle horizontally. All right. Second column, we have, we're going to deal with a constant k sub 2 now, and we're going to let x be our k sub 2. So when we do that, what are we looking at? We're looking at z is equal to k sub 2 squared plus y squared. And this ends up just being a parabola. So how is it a parabola? Again, this is a constant. And so think about this as a vertical shift up X amount of units, okay? And then we have our nice quadratic y squared with the vertical shift going up, as long as k is positive. K is negative, it just goes down. So our vertex here would be just 0, comma, k sub 2 squared. And then this is going to be a vertical level trace. So our horizontal is our circle, and then our parabola is a vertical. Okay, and then last but not least, let's look at our y being k sub 3. And when we do that, we're looking at our equation z is equal to x squared plus k sub 3 squared. And we once again have another vertical level trace of a parabola formed with our vertex at 0, k sub 3 squared. And so if we were to sketch this out again, I am not the greatest when I'm graphing three-dimensional structures, so you might not be able to see it quite well through my visual, with the pink and the yellow being like the parabolas, and then that purple circle being that horizontal circle. So I also put it into, I don't think I put this into GeoGebra. I put this into probably ChatGPT. And so when I did that, this is what we got, which is a much better way to visualize it. You really see this horizontal level trace as our circle, and then our vertical level traces with our parabolas forming, like, think about like, I don't know, a piece of paper scooped in like a bowl. And then another way to really look at them separately, the vertical level traces and the horizontal level traces, are through these visuals, where we have our YZ trace as our parabola, our XZ trace is also a parabola, and then our XY trace is a point. And then if our z is equal to k, then our trace is a nice circle. So now when we put this all together, we get this surface. The surface z is equal to x squared plus y squared. Okay. And then this is the GeoGebra 3D visual. Okay. So we have some more notes. What is a quadric surface? And looking at the general notation of it. So this first part, we have the graph of a second degree equation in two variables, can be represented as ax squared plus bxy plus dx plus ey plus f being our constant, is equal to 0. How do we know it's a second degree? That highest degree is of degree 2. And this is a conic section. So whether we're talking about a parabola, an ellipse, or a hyperbola. And then if we're looking at it in terms of 3 variables now, still highest degree being 2, we have the following. And so in 3 variables, it's called a quadric surface. Okay. There are 9 different types of quadric surfaces. So as with our conic sections, when the equation of a quadric surface is written in the form, I should use a different color here. Why don't we do red? We have our whole ax squared plus by squared plus cz squared plus dxy, exz, fyz, gx, hy, iz, j is equal to 0. So this is our general form. Okay. Bringing back to our whole completing the square, which you guys have learned in your college algebra class, or in high school, or in pre-calculus. You practice it a lot in calculus. It's back here in Calc 3. So how do we put things in standard form? We once again complete the square. The equations we consider here are in standard form. and the corresponding quadric surfaces are centered at the origin of an XYZ coordinate system. And so also it's important to point out that quadric surfaces are characterized by their intercepts. So that's why it's so important to find their intercepts and find their traces, which we've practiced twice already now. So now we're on to identifying quadric surfaces based on an ellipse, which is our second objective for today. And so the first three quadric surfaces we investigate are based on an ellipse. And each of these surfaces has at least one trace that is an ellipse. And so our definition of an ellipsoid, this is our general equation, our x squared over a squared plus y squared over b squared plus z squared over c squared is equal to 1. And all of our constants a, b, c are positive. So in this general form, we can get the intercepts of the ellipsoid to be plus or minus a comma 0, 0, 0 comma plus or minus b comma 0, and last but not least 0, 0 plus or minus c. And then again, the traces of an ellipse or the traces of an ellipsoid are ellipses. Some more notes. The difference between an ellipsoid of revolution and a sphere is the fact that in a sphere, all your values A, B, and C are equal. Whereas in an ellipsoid of revolution, only 2 of those 3 values are equal to one another. So you'll see like our blue ellipse and our pink ellipse are identical in the values of the semi-axes, whereas in the sphere, all of them are, all 3, including that green circle. Whereas here, the green circle is different. Right. Another figure, we have our elliptic cone. It's our second quadric surface that we're going to be talking about based off of an ellipse. And the general form is z squared is equal to x squared over a squared plus y squared over b squared. Both a and b are positive. I also highly recommend you guys create like flashcards and draw out these figures so that you can really reinforce the general formulas to the visualizations. And so some properties for our elliptic cone, we have the only intercept is the origin, and it's called the vertex of the cone. Our trace on our XY plane is our origin. And our traces are parallel to the XY plane. Those are known as ellipses on the z-axis. And so let's see, is there anything else? I kind of want to show you. Yeah, these are our ellipses on our z-axis. And then the trace in the YZ plane consists of the pair intersecting lines z is equal to plus or minus y over b. The trace in the xz plane consists of the pair of intersecting lines z is equal to plus or minus x over a. So some famous properties. We have a circular cone, and a circular cone is created when our a and b are identical to one another, and then the traces are circles. And so down below here are just other forms of elliptic cones with their restrictions on A, B, and C being positive. We have an elliptic paraboloid, our third quadric surface based off of our ellipse. And this is our general equation over here. Our z is equal to x squared over a squared plus y squared over b squared, where both a and b are positive. So you can sort of see that our elliptic cone and our elliptic paraboloid are very similar to one another. And so the properties is where there are some differences. It has, once again, one intercept, the origin, also known as the vertex. The trace of an elliptic paraboloid in that xy plane is the vertex. And the traces parallel to the xy plane are ellipses. So like we have that here. The traces in the other two coordinate planes are parabolas. So you can see that over here. And we have our z is equal to y squared over b squared in our yz plane, x squared over a squared in our xz plane. And then last but not least, our traces parallel to the xz and yz planes are, once again, parabolas, which we've already stated. Okay. So just keep in mind, elliptic paraboloid, we have z is equal to this mumbo jumbo, and then an elliptic cone, it's z squared is equal to this mumbo jumbo. Okay, cones have a top and a bottom portion, hence the z squared. Right. Our paraboloid of revolution. So if we have our A and B values equal to one another, then we get this paraboloid of revolution. And the traces parallel to the XY plane are circles. So I demonstrated that above here, but we can like repeat it as we go all the way down to create this elliptic paraboloid. And then last but not least, these are just other forms of an elliptic paraboloid where the different x, y, and z's are being squared. Okay. I don't think this was covered up, so let me cover it for you guys. Okay, much better. So we have our example 3, and we want to identify each quadric surface and then list its intercepts and its traces in the coordinate planes. So part A, we're given 4x squared plus 9y squared plus z squared is equal to 36. And so straight off the bat, you know that we're dealing with an ellipsoid. We just need to manipulate it to that proper general form, x squared over a squared plus y squared over b squared plus z squared over c squared is equal to 1. So how do we do that? How do we go from 36 to 1? We just divide everything by 36. And so that's what we're doing. And when we do that, 4 divided by 36 is just 1 over 9. So we get x squared over 9. And then 9 divided by 36, that's 1 over 4. So we get plus y squared over 4. And then plus our z squared over 36 is equal to 1. Now we know that what do we have here? What quadric surface? We have an ellipsoid. Next, let's identify the intercepts. So when x and y are equal to 0, what is our z? So 0, 0. Multiply that right-hand side by 36. Take the square root. Oops, sorry. Take the square root. and we get plus or minus 6. So for the z-intercept, we have 0, 0, minus 6, and 0, 0, plus 6. All right, our next intercept is going to be our y-intercept. So we're going to let x and z be equal to 0. And so when we do that, we get our y to be plus or minus 2. So 0 plus or minus 2, comma 0. And then last but not least, we want to find our x-intercept. So when y and z are 0, so we have 0, 0, and then x is plus or minus 3. So we get plus or minus 3, comma 0, 0. Let's go ahead and do part B, where we figure out what quadric surface we're talking about, and then we identify the intercepts before we go on to the next slide, where we'll be finding the traces for both our problems A and problems B. And then I'll once again show you guys a visual of what that looks like. So in part B, we have our x is equal to y squared over 4 plus z squared. So we're going to be dealing with an elliptic paraboloid here, right? We have this z squared, and then we can bring everything else sort of over. And in terms of looking at our x, y, and z intercepts, let's first start off with our z-intercept. So let's make x and y be equal to 0, and then we get just 0, 0, 0. If we are going to look at our y-intercept, we want to set x and z equal to 0, and we once again get 0, 0, 0. And last but not least, if we want to look at our x-intercept, we set y and z equal to 0. And when we do, we once again get 0, 0, 0. So what does this tell us? This tells us that our only axis intercept is at the origin. And it also tells us when we're dealing with an elliptic paraboloid, we have our vertexes at the origin, 0, 0, 0. And then I'll write down here our whole general form of an elliptic paraboloid based off of these variables. So general form of we have our x is equal to y squared over a squared plus z squared over b squared. Okay, so it's actually in that perfect form to be able to identify it. And then I think the last thing on this page was just showing us that our parabola is going to be opening up in that positive x direction. Okay. So now let's look at our ellipsoid and our oh my gosh, I forgot, our elliptic paraboloid, and find the traces of them. Okay. So what's our first step? Let's first look at the ellipsoid, and what do we want to do? We want to look at our xy plane. So when z is equal to 0, what are we dealing with? And so when z is 0, this whole thing cancels out, and we're left with our x squared over 9 plus y squared over 4 is equal to 1, which is our famous ellipse. We have those semi-axes. Square root of 9 is that plus or minus 3, and square root of 4 is plus or minus 2, which is that note that was highlighted in green before. And now we can move on to the next one. So our xz plane, now when y equals 0, what are we left with? We're left with x squared over 9 plus z squared over 36 is equal to 1. Once again, we have an ellipse. Semi-axes are 3 and 6 here. YZ plane, we have y squared over 4 plus z squared over 36 is equal to 1. And so another ellipse we're dealing with our semi-axes at 2 and 6. And so what do we know based off of the traces for our ellipsoid? Well, we know that every coordinate plane has the trace to be an ellipsoid. And then once again, that full surface is bounded by an ellipse. Okay, so traces are an ellipse, full surface ellipsoid. Now let's look at our elliptic paraboloid. And so same exact concept, we'll have z equal to 0. Then we have x equals y squared over 4, which is just basic parabola with the vertex at the origin. When y equals 0, we once again have a parabola, our famous parabola, x equals z squared. So vertex once again at the origin. And then when x is equal to 0, we get 0 is equal to y squared over 4 plus z squared. And so we only have one solution here. We have the trace at that single point 0, 0, 0. And our only solution is when y and z are equal to 0. So let's look at these examples from a visual standpoint. For A, we have our ellipsoid, which looks like this guy. And I'll show you again the interactiveness in a moment. And then our part B, for example 3, is our elliptic paraboloid, which looks like this guy. Okay, so let me stop recording and then share my laptop screen so you can see it in a bit more detail. Okay, so this was our example 1 for the lesson. Example 2, I don't know if I showed you that one, our circular paraboloid from our different angles. Quite basic. Example 3A is our ellipsoid. Let's see it from all different angles. And then example 3B is our elliptic paraboloid. Okay. Really quite cool doing this. All right, let me stop recording. Okay, so let's continue. We have our third objective, where there are 3 quadric surfaces that are based on hyperbola. So we went over the 3 based off of ellipses. Now we are going to do 3 based off of a hyperbola. And then something to just take note of, each of these surfaces has at least one trace that is a hyperbola. So that is a cool thing to just keep in your back pocket. So our first one, we have our hyperbolic paraboloid, where our general definition is z is equal to y squared over b squared minus x squared over a squared. Both a and b are positive. And we have the origin is our only intercept of the hyperbolic paraboloid. Our trace in the xy plane is in the pair of our lines y over b is equal to plus or minus x over b. which intersects at the origin. You can see that over here. The traces parallel to the xy plane are hyperbolas given by the equations y squared over b squared minus x squared over a squared is equal to k, where our z is equal to k. And then the trace in the xz plane is the parabola z is equal to x squared over a squared. So our xz plane right here, we have the parabola taking place right there. And it's opening downwards. The traces parallel to the xz plane are also parabolas that open down. And then last but not least, we have the trace in the yz plane is the parabola z is equal to y squared over b squared. So our yz plane is this parabola here, which opens up, and the traces parallel to the yz plane are also parabolas that open up. We want to notice that the origin is the min point for the trace in the yz plane. This is our minimum, sort of like our saddle seat. And the max point for the trace in that xz plane. So notice how when we're looking at the xz plane, it's that maximum, which is kind of cool. Because of the graph's appearance, the origin is called a saddle point of the surface. So I kind of just said that a few seconds ago, kind of foreshadowing up until this point. And then these are just other forms of a hyperbolic paraboloid. We have our hyperboloid of one sheet. Our visual representation looks like kind of like a cylinder, but a cylinder that wants to be skinny, and so they're sucking in at the stomach. And so our general form is our whole x squared over a squared plus y squared over b squared minus z squared over c squared is equal to 1. Once again, a, b, and c all positive. These are some of the characteristics. Intercepts plus or minus a, 0, 0, 0 plus or minus b, 0. Our trace in the xy plane we have as follows, and all traces parallel are ellipses. Trace in the yz plane we have as follows, and the trace in the xz plane is the hyperbola. So our xz plane, right, this is where our hyperbola is. And then we have traces parallel to the yz and xz. So yz and xz, xz are also hyperbolas. The z-axis is called the axis of the hyperboloid of one sheet. Right. Keep going. If we have our A equal to B, then we have the surface known as a hyperboloid of revolution. And so this tells us that we're dealing with a circle up here, but all of these hyperbolas have that same distance. Okay, whereas if you notice over here, our base over here is an ellipse, not a circle. So these are going to be of different, like, I shouldn't say distance, like different curvatures. Okay, these are all the same. And these are other forms of a hyperboloid of one sheet. Hyperboloids of two sheets. So notice how we no longer have this cylinder that's sucking in at its stomach. We have just two separate sheets that think about like polarized magnets. They are trying to get away from each other. If you like set one magnet on the table and then the other magnet on top with the opposite magnetic force, then it's going to be elevating in the air. And that's very similar to what's being represented here. So we have a hyperboloid of two sheets is shown in this figure. Our intercepts 0, 0, C and 0, 0, negative C consist of two parts when Z is greater than or equal to C and less than or equal to negative C. And then if Z is 0, the equation has no real solution, right? Never hits the origin. So we have no trace in our XY plane. Traces parallel to the XY plane are ellipses and are defined for absolute value of Z is greater than C. And we have the traces in the YZ plane and the XZ plane are the hyperbolas. So our Z squared over C squared minus Y squared over B squared equals 1, and then our Z squared over C squared minus X squared over A squared equals 1. Our traces parallel to these are also hyperbolas. And then the Z-axis is called the axis of the hyperboloid of two sheets. These are other forms of a hyperboloid of two sheets. And then finally, we arrive at our example 4. And so we want to first identify these quadric surfaces, find the intercepts, and then on the next slide, we're going to find the traces for both of these quadric surfaces. So let's get it into a familiar form. Let's divide both sides by -9 first in part A. And then when we do that, let's put it in fractional form and simplify any negatives, and we get negative x squared over 9 plus y squared over 9 minus z squared over 9 is equal to 1. And so straight off the bat, this is our last example or last set of notes that we were talking about, where we have a hyperboloid of two sheets. And just so you guys can see, right, both the x and z's are negative, and well, we should really put in a third step here. Make that right-hand side equal to -1. So we're really looking at positive x squared over 9 minus y squared over 9 plus z squared over 9 is equal to -1. And so that would be this form right here. Okay. Right, let's find our intercepts. So first one, when y is equal to 0 and z is equal to 0. So y equals 0, z equals 0, and we get negative x squared is equal to positive 9. That's not possible. So we have no solution for this case. Let's now try for when x is equal to 0 and y is equal to 0. And you'll notice very quickly that we also have a no real solution here. But we do have a solution for our y-intercept when x and z are equal to 0. we end up getting y squared is equal to 9 when we bring that 9 over, and the square root of 9 is plus or minus 3. So we have 0 plus or minus 3 and 0, and we're done. Okay. Let's move on to part B before we find the traces for A and B. And so z is equal to x squared over y minus y squared over 4. Z is equal to this. Okay, so what do we have? We have our hyperbolic paraboloid. And let's see if I can go back to that general form. Our hyperbolic paraboloid. Right, it's in its perfect form. So now let's go back. Let's identify the intercepts. First one, x-intercept. So when our y is equal to 0 and z is equal to 0, we get x squared is equal to 0, which means x is 0, so 0, 0, 0. Great. Now let's find our z-intercept. So when x and y are 0, we also get 0, so we get 0, 0, 0 for our z-intercept. Okay. And then the last one is finding our y-intercept. So when x and z are equal to 0, what do we get? So z is 0, x is 0. We once again get y is 0, so 0, 0, 0, which tells us that our only axis intercept is the origin. Okay, so now what we're going to do is we want to find the traces. So I'm going to go over to the next slide, and we have our hyperboloid of 2 sheets for our part A, and then we have our hyperbolic paraboloid for our part B. And so in our first case with part A, we're going to look at our xy plane when z is equal to 0. So plug in 0 for z, and what do we end up getting? We get negative x squared over y plus y squared over, I said over y, I meant 9, plus y squared over 9 is equal to 1. And then what can we do from there? We know that we're dealing with a hyperbola, which is opening up and down along our y. If you wanted to bring the 9 over, you can, but I honestly think it's way easier to see it from this side. Okay. How do we get that? There we have it. And then you can also see it as pulling out a negative and looking at x squared minus y squared is equal to negative 9. It's probably the clearest way to see it. Our xz plane, when y is equal to 0, what do we end up getting? We get our, y is equal to 0, negative x squared over 9 minus z squared over 9 is equal to 1. So I'll reveal that. And then let's multiply both sides by 9, and we get negative x squared minus z squared is equal to 9. And then also let's divide both sides by -1, and we get positive x squared plus z squared is equal to -9. But straight off the bat, like, you can see that this is a contradiction, because anything squared plus anything else squared, when we're dealing with the real number system, would get you a positive value. And because it's negative here, we know that we have no real solutions. It's an empty empty trace. And then finally, we have, let's take a look at our YZ plane where x is equal to 0. And when we have x equals 0, this whole thing up here cancels out. And so we're looking at y squared over 9 minus z squared over 9 is equal to 1. Multiply both sides by 9, and we get y squared minus z squared is equal to 9. And so this gives us a hyperbola opening along our y. So the full surface, once again, as stated on that previous slide, it's a hyperboloid of 2 sheets, and it's along our y. Now let's look at our traces for our z is equal to x squared over 9 minus y squared over 4. When z is equal to 0, what do we end up getting? We get x squared over 9 minus y squared over 4 is equal to 0. Let me see. And then what does this tell us? We can also put it as x squared over 3 squared minus y squared over 2 squared. So you can really see those semi-axes at play. And then what you can do, well, it's not a semi-axis because this is minus. What we want to do is, why don't we find what y is? Let's see if we can do some isolation here. So we're going to go ahead and add y squared over 2 squared to this side. And when we do, we get y squared over 2 squared, also known as y squared over 4, is equal to x squared over 3 squared. So let's show that. And then let's multiply both sides by 2 squared. So we get y squared equals 2 squared x squared over 3 squared, so that when we take the square root of both sides, we get our y is equal to plus or minus 2x over 3. And so we have a pair of intersecting lines through our origin, 0, 0. Okay. Our xz plane, our y is equal to 0 here. What do we end up getting? Z is equal to x squared over 9, which is a basic parabola that stems at the origin. The origin is our vertex here. And so we have a parabola opening upward in the z direction along x. And then finally, our yz plane, when x is equal to 0, we once again have another parabola, but now it's going to be opening downward because our z is going to be negative y squared over 4. And so we have a parabola opening downward in the z direction along y. So for our hyperboloid of 2 sheets along y, our visual looks something like this. And then I'll show you the interactiveness in a moment. And then for our hyperbolic paraboloid, we have our visual is going to look something like this. And then once again, I'll show you the interactiveness right now, actually. Right, so this is our hyperboloid of 2 sheets, our example 4a. Just rotating it so you can see like all of the angles. And then we have our hyperbolic paraboloid, which is our example 4b, which is this guy here. All right, see that? Saddle. Probably a better visual. Okay, I'll zoom out a little bit. It's really accented a bit more here. Cool. All right, let's stop recording. All right. So now we're on our fourth objective. And so this part is being able to identify cylinders. And so the last three quadric surfaces that are remaining are cylinders. And the standard equations are characterized by the fact that one of the variables is missing from the equation. So why don't we highlight that? In naming these surfaces, we've chosen z to be that missing variable. And so as a result, z is an unrestricted variable. So these cylinders will be unbounded in that z direction. Cylinders are surfaces that are generated by a line moving along a plane curve while remaining perpendicular to the plane. We've seen cylinders ever since grade school. And cylinders are named for the trace in the plane in which the unrestricted variable is 0. So in the xy plane, our z is 0. Okay. Our first cylinder that we're going to be talking about is our parabolic cylinder, which has the general equation x squared is equal to 4ay. And so our a, obviously, we have excluded or restricted. It cannot be equal to 0. And so this parabolic cylinder does not include the variable z, so the trace in that xy plane is our parabola x squared equals 4ay. The surface is generated by moving a line along the parabola while remaining perpendicular to the plane containing the parabola. And it can be visualized by just taking a sheet of paper and bending it so that an edge of the paper traces out the portion of the parabola, as demonstrated in this visual up above over here. Our second cylinder that we're going to talk about is our elliptic cylinder, where our general equation is x squared over a squared plus y squared over b squared equals 1. Both a and b is positive. Think about taking a piece of paper and folding it into that cylinder visualization, and boom, you have your elliptic cylinder. The trace of the xy plane is an ellipse with the center at the origin. The surface is generated by moving a line along the ellipse. Our whole x squared over a squared plus y squared over b squared is equal to 1. While remaining perpendicular to the plane containing the ellipse. And then an elliptic cylinder can be visualized by, again, taking that sheet of paper and attaching, like going that full length across, or thinking about like a toilet paper roll with the whole inside of the toilet paper being empty. Okay, if A is equal to B, then the trace in the xy plane is a circle, so think about this being a circle. And the cylinder is known as a right circular cylinder with radius A. And then the last cylinder that we're going to be talking about is our hyperbolic cylinder, where we have our general equation as x squared over a squared minus y squared over b squared is equal to 1, both a and b being positive. And so we have this representation up above over here, really getting to see those hyperbolas, but in a cylindrical format. And so the surface is generated by moving a cylinder along one branch of the hyperbola while remaining perpendicular to the plane containing the hyperbola, and then repeating the same procedure on that second branch. We have our intercepts plus or minus a, 0, 0. The hyperbolic cylinder consists of two parts. Neither of them are touching that z-axis, and it can be visualized by bending two pieces of paper so that the curved edges trace out a portion of a hyperbola. And now we arrive at our example 5. And so we're given identify the cylinder defined by the equation y squared is equal to 8z and describe how it can be generated. And so our variable x is missing in this equation, and that means that the cylinder extends infinitely along our x-axis. So that's the first thing that we want to point out. And then the second thing that we want to note is, okay, the cross section. And so with the cross section of the cylinder in that YZ plane, we have y squared is equal to 8z, setting our x equal to a constant. Now, what form is this in? If you noticed, this is in our parabola sheet form, where you take a sheet of paper and you bend it upwards. We have that parabolic cylinder where it's like y squared is equal to our what was the variables that they used? AY, for AY. I feel like I use P instead of A a lot of the time. And they had it as x squared. Sorry, we had two variables. So let me reveal this. So we have this parabola opening upwards in the z direction. And so what do we have? We have a parabolic cylinder, which is parallel to our x-axis, because that's that missing variable. And so our y squared equals AZ, or 8z, defines the shape in the YZ plane. And again, our standard parabola form is the whole x squared equals 4ay, or you can have it y squared equals 4pz. The a acts as a p. But if you are solving for your a or for your p value, you just have to set 8 equal to 4p, and then you get your p-value is equal to 2. And so the second part of this question is asking us, describe how it can be generated. And so how do we sort of create this visualization? And so on the next slide, I have the whole step-by-step procedure. The first one, we want to draw our x and y and z axes. Then in our YZ plane, aka our x is set equal to 0, we sketch out our 1/8 y squared, and that's because we want to look at it as a parabola. And so 1/8 y squared represents that parabola, which stems from our origin, 0, 0, 0. So that's our second step. And then we want to extend that parabola along the x-axis in both directions. And then last but not least, Our resulting surface is our parabolic cylinder that is opening upwards along our Z and extends infinitely along our X. And so you can see a nice, beautiful visualization over here. And now what I'll do is I'll share my computer screen so you can see this visualization from all different angles. So here we have it. And then we can look at it from the top view, side view. Yeah. So it really legit looks like just a sheet of paper that is bent upwards in a parabola form. Okay, so I'm going to stop recording this again. All right, so let's continue. We're on our fifth objective, which is our second to last objective, where we're asked to identify and graph our quadric surfaces. And so we have the table shows computer-drawn graphs of the 6 basic types of quadric surfaces in standard form, which you're going to see on our next slide in a moment. All surfaces are symmetric with respect to the z-axis. If a quadric surface is symmetric about a different axis, its equation changes accordingly. So why don't we highlight that last part? Maybe we'll highlight this part too. And again, the 6 basic types of quadric surfaces in standard form, which is what we have here. Our ellipsoid, our elliptic paraboloid, our hyperbolic paraboloid, our cone, our hyperboloid of 1 sheet, and then our hyperboloid of 2 sheets. And then we have the equations over here, what the traces are from a visual standpoint, and then if our A, B, and C were set to certain values, does that create something else? Looking at both horizontal, vertical traces, and I think that's it. And I guess with the hyperboloid of 1 sheet, the axis of symmetry, how that corresponds to the variable whose coefficient is negative. So just a lot of characteristics. Another slide of notes / comments. Quadrics in general are best graphed using CAS, which is, again, a computer algebra system, so that you can really see it in that 3-dimensional world. And then comparing the given equation to those discussed in the section helps to identify the graph. So here are some suggestions to help make the comparison. You want to remember that equations of quadric surfaces listed are given in standard form. Interchanging the variables does not affect the classification, and it only affects the orientation of the quadric surface. So it's our first suggestion. Our second, we have cylinders are characterized by a variable missing from the equation. It's a really good one to, again, keep in your back pocket. And then the third suggestion, the technique of completing the square is sometimes required to identify the given quadric surface. So in this case, a translation of axes will help to find the correct location of the graph. And we'll soon see that in our example 6, both A and B, where we may or may not have to complete the square for both or for one of the problems. Okay, so our example 6, we're asked to identify the surfaces represented by the given equations. Our first one, we have 16x squared plus 9y squared plus 16 Z squared is equal to 144. And so how do we put this in standard form? We're first going to divide everything by 144 so that we can get this right-hand side equal to 1. And so when we do that, we end up with 16 divided by 144, which is just 1 over 9. And then 9 divided by 144 is 1 over 16. And then we have, once again, 16 divided by 144 is 1 over 9. So we have x squared over 9 plus y squared over 16 plus z squared over 9 is equal to 1. And so you can very clearly see x squared over a squared plus y squared over b squared plus z squared over c squared is equal to 1. What does that give us? Our quadric surface is an ellipsoid. And so it's centered at our origin, and then our semi-axes are, well, we have square root of 9, so 3 in the x direction, 4 in the y direction, and 3 again in our z direction. Okay. Let's look at this using a CAS, computer algebra system, to see this ellipsoid in our 3D world. And so this is a nice sketch of it. And then what I'll do is I'll again show you the interactive visualization of this. Right, so here we have it. We can just rotate it about so you can just see it from all different angles. And yeah, cool. Okay, so now let's look at part B, where we're given 9x squared minus 18x plus 4y squared plus 16y minus 36z plus 25 is equal to 0. And we want to figure out, okay, what quadric surface are we talking about here? The hint was on 2 slides prior where we might have to complete the square. And so what do we do here? Well, I see an x squared and I see a y squared, and then I see this 36z. I'm going to bring that 36z over to the right-hand side and then pair all of my x's and my y's together and then go from there. And so you end up with 36z is equal to 9x squared minus 18x. I'm going to create a little bit of space, plus 4y squared plus 16y, and then a little bit of space, plus 25. And now we can clearly see, okay, how do we complete the square with these two quadratics? Well, negative 18, you could divide that by 2 and square it, or you can factor out a 9 from each of the terms. So we have 9 in parentheses, x squared minus 9, and then leave space. And then it should be x squared minus 2, and then leave some space. And so now when you divide, and it should be minus 2x, when you divide our negative 2x by 2, that just becomes negative 1, square it, and then you have a plus 1 here. Okay. And then for our other situation, let's factor out a 4. And we're left with y squared plus 4y. Divide 4 by 2, square it, and you get a plus 4. And that finishes up that part. Okay, and this is all equal to 36z. The last thing you want to be mindful of is we added this plus 1, but technically 9 is being distributed. So we really added a plus 9, which means we have to subtract 9 so we can keep everything balanced. And same with here. We added 4 times 4 is 16. We're going to subtract 16. 25 minus 9 minus 16 is just 25 minus 25. So this all actually ends up canceling out. So let's show that, which is what we have over here. And now we can officially complete the square, our x squared minus 2x plus 1 is just the same as x minus 1 in parentheses squared. And then our y squared plus 4y plus 4 is the same as y plus 2 in parentheses squared. And then once we have that all set up, we can go ahead. Well, let me show you this first. Then what we can do is to put it into that elliptic paraboloid form, why don't we divide everything by 36? 9 divided by 36 is 1/4, and 4 divided by 36 is 1/9. So we end up with z is equal to x minus 1 in parentheses squared divided by 4 plus y plus 2 in parentheses squared, all divided by 9. This clearly shows the form of our elliptic paraboloid, which is opening in the positive z direction and then has our vertex at 1, -2, 0. Okay. So from a visual standpoint, we get this elliptic paraboloid opening up in that positive z direction. And then now let's show it using the GeoGebra interactive computer algebra software. So here we have it. We rotate it. It's a nice angle right there. Here's kind of cool too. Honestly, I feel like I had it. The best angle was when I screenshotted it the first time. Yeah. All right. All right. So we finally arrive at our last objective for today, and this is finding the curve of intersection of two surfaces. And so in this section on lines and planes, we learned how to find the parametric equations of the line of intersection of two planes. So I'll highlight that. And now we extend the idea to finding the parametric equations of the curve of intersection of two surfaces. So our method, when two surfaces in three-dimensional space intersect, their intersection forms a curve. And so when two surfaces, we'll use green, intersect, their intersection forms a curve. To find its parametric equations, we want to follow these two steps. So the first one is we combine the two equations, for example, by substitution, to eliminate one variable and express one variable in terms of another. And we'll see this in a concrete example on the next page. And then the second, we are going to introduce a parameter t and write each variable in terms of t. So giving equations of the form x is equal to x of t, y is equal to y of t, z is equal to z of t. Okay. So now that we know this, why don't we take a look at our example 7, where we have find the parametric equations for the curve of intersection of the cone z is equal to the square root of x squared plus y squared, and the plane z is equal to 1 plus y. And so first, what are we going to do? We are going to set them equal to each other. So we get square root of, let me see, x squared plus y squared is equal to 1 plus y. And then just to note, we're going to have our 1 plus y be greater than or equal to 0. And we're going to have this hold for the parameterization. Okay. And now let's solve. We want to eventually isolate our y. So first step, square both sides. Then we get x squared plus y squared is equal to 1 plus y in parentheses squared. Then we're going to go ahead and we are going to factor this right-hand side. So that becomes 1 plus 2y plus y squared. And then we'll subtract y squared from both sides, which ends up canceling out the y squareds, so that we're left with x squared is equal to 1 plus 2y. And then we'll utilize our inverse operations, subtract 1 from both sides, and divide both sides by 2. So we end up with y is equal to x squared minus 1 over 2, which can also be written as the product of the binomials x plus 1 times x minus 1 all over 2. And now we can do the substitution of z back into it. We know that z is equal to 1 plus y, and we know that y is this whole x squared minus 1 over 2. So we get z is equal to 1 plus x squared minus 1 over 2. But 1 as a fraction with a denominator of 2 is just 2 over 2. So we end up with 2 plus x squared minus 1 all over 2. And then 2 minus 1 is just 1. So last but not least, we have z is equal to 1 plus x squared, or you can write x squared plus 1 all over 2. Right? So there we have it. That was our first step, expressing one variable in terms of another. And now the second step is introducing the parameter t and writing it in that sort of function notation form. And so again, we're going to let x be equal to t here. So our x of t is t, our y of t is this whole t squared minus 1 over 2, and then our z of t is t squared plus 1 over 2, where t represents all the numbers in the real number system. And so in vector form, we just have t comma t squared minus 1 over 2 comma t squared plus 1 over 2. And then you can always check to make sure that everything pans out. And so the square root of x squared plus y squared, in terms of t, we have the square root of t squared plus, in parentheses, t squared minus 1, close parentheses squared all over 4, is equal to our z, which is t squared plus 1 all over 2, and this is equal to our 1 plus y. And so this indeed does work. So we have that this parameterization satisfies both surfaces. And we're done. So in terms of really seeing the visualization of this, we have it on this next page. And then I have also another angle of the visualization. So you can very clearly see the cone on that first visual. You can see the plane too, but on the second visual, you can see where the plane is intersecting the cone and how this parabola is formed. Okay, I'll also show you guys the interactive visual as well. Right, so let's move it around. You can see our plane and our cone very vividly here, and where they intersect, what is formed. It's really kind of cool. I think this one's the coolest one so far. But yeah. Okay. let's do another example. And this is going to be our last example for this lesson. So we have find the parametric equations for the curve of intersection of the paraboloid 4y is equal to x squared plus z squared, and the plane y is equal to x. So our first step is we know y is equal to x, so why don't we sub this in to our 4y equals x squared plus z squared equation. So wherever we see a y, we're going to change it into x. And so when we do that, we end up with 4x is equal to x squared plus z squared. And then let's we're going to isolate our z squared, and we're going to bring the x's all over to one side. And so we get z squared is equal to 4x minus x squared. And so our next step is we are going to see if we can complete the square with this quadratic function. I personally don't like negative values for that leading coefficient. So what I'm going to do is I'm going to actually first factor out a negative. And when I do, I have negative in parentheses x squared minus 4x, and then close parentheses. And then from here, our special key, negative 4 divided by 2, that gives you negative 2, square it, and you get 4. And so that's why we're adding 4 to both sides. So this whole x squared minus 4x plus 4 is just factored into x minus 2 in parentheses squared. And so that's what we have on this next line, x minus 2 in parentheses squared. And so now what we can do is, now let's get the constant by itself. And so we're going to add x minus 2 in parentheses squared to both sides. And so when we do that, we get our z squared is equal to, or sorry, our z squared plus our x minus 2 in parentheses squared is equal to 4. And we have that rewritten down here as well, a little bit more cleaner. So what does this tell us? We have a circle that is centered at 0, 2, and has a radius of, what's the square root of 4? 2. All right. Centered at, I said 0, 2. Oh, 2, 0, because this is our x value. Laser. Yeah. In the x, the z plane. Great. And so now let's look at, we're talking about a circle here. So we want to think about a good or a convenient parameterization. And so with circles, we have one full revolution around a circle is 360 degrees, but in terms of radians, we have 2 pi. So we want to sort of think about, okay, what are functions that have this sort of cyclical notion? First thing that comes into play are our sine and cosine functions that have those bounds, but then also the unit circle, where in polar coordinates we have our x comma y are cosine of theta comma sine of theta. So we're gonna put it in terms of our sine and cosine. And so what is our x value here? Our x of t is just going to be 2 plus cosine of t. And so how do we find this? We sort of want to think about it as our trigonometric identity, which stems from our sine squared. I'll put it in terms of t since that's the variable we're using. Sine squared t plus cosine squared t is equal to 1. But we have different conditions here. Our condition for our radius is not 1 here. It's 2. 2 squared gives us our 4. And then we want to figure out, okay, well, what manipulation do we need to do in order for it to suffice here? And so we set our x of t parameter to be 2 plus 2 cosine t, because when we plug that in over here, the 2's will cancel out, and then we're just left with 2 cosine t squared, which ends up giving us 4 cosine squared t, okay? And then our z squared, well, we want it to be some form of sine squared t. How do we get 4 sine squared t? We have our z of t to be 2 sine of t, because when we square that, we get our 4 sine squared t. And then what about our y? Our y of t, we can set equal to, it's the same as our x from the question at hand. Our y is equal to x, so it's the same, 2 plus 2 cosine t. Okay, so now when we put that in, we end up with 4 sine squared t plus 4 cosine squared t is equal to 4. Divide everything by 4, and boom, we're back to our famous trigonometric identity. Okay. And again, our t is representing all of our values in the real number system. So last but not least, let's take a look at a visual representation of this. We have a nice cylinder taking place over here, and then we have our plane intersection. And I also put in our parameters in our vector form, where again, we're talking about circular notion here, where a circle goes from 0 to 2 pi, from radian format, or 0 to 360 degrees. I'll show you another sort of different perspective on this, which is over here, but then I'll also share my screen so you can see it more interactively. Okay, and so here we have it. I'll show you all the angles. It's a good angle. And yeah, okay. And so that was the last example for this section. We've completed our quadric surfaces. I hope this was helpful. Let me know if you have any questions, and I will see you guys again soon. Take care.